Industrial hygiene, gas and vapors, lab number 5. Okay, starting with this is the passive monitor, which is practical exercise number 1. If you notice, the units of scale are right here. It's a little blurry, but you can see that percent, and there's a dash, and it kind of goes over here. If you look right here, it says percent dash hour. Those are the units of our tube, okay? This is an intact. You can see the little score marks where you break it off, and you can see that part's missing here. This is the open part where the gases diffuse, okay? And you can see this is an open exposed tube. You can see the color change from the blue to the white. You can see how it's starting right here. You kind of have your transition, okay? And here's the percent volume in the hours are kind of off to the edge here. The tube used, it's actually upside down, is a carbon dioxide 1%/A-D. The D stands for diffusive tube. So with this tube, we're only opening the one end. It's got the little mark there to remind you where to break it at. And it sits, the length of time determines the amount absorbed. So again, you can see there's that H for that hour. Here's the passive that I want you to read. You'll see some closer ups of it before, a little bit later. You can see the color change. Now the color change, you kind of have to estimate where that's going to be within the slide. So I give you multiple pictures to try to get a feel for where that stain front is. You have to do 2 estimations. You have to estimate where you think the stain front is, and then since the stain is in between 2 markings, you have to estimate where you think that average stain front is between those 2 markings as well. The sample was collecting in the breathing zone. The collar is actually closer on the collar, but you needed it for a good picture. You can kind of see it sits in the holder like that, just clip to the collar. Again, there's your units of scale, volume, percent, hour. Here's our tube. This is the one that was exposed for you to try to read. You can kind of look at where you think that stain front is relative to the scale, and based on where you think the color of that stain front is, that's your reading in percent hours. You'll get the hours from the question results thing. There's a number of different hour time frames that I have. This will be the data for table 1. This will fit in the amount collected, which you read off of this. The hours you'll get from the question, and then from the hours that you have and the reading you have, you'll get the concentration. Basically, it's percent hours divided by your time gives you your reading in percent. And the units are carbon dioxide. Here's a little bit better view of kind of where that stain is. Again, this is the same tube. So try to look at those different tubes and as best estimate where you think that stain front is. So that's practical exercise 1, which is a passive sampler. Practical exercise 2, we're going to use a Dreger pump and Dreger tubes. You don't mix and match tubes. We're going to use 2 systems. We're using Dreger for practical exercise part 2, A and B. And then when we do the tubes later on for our bag sample, they will be Gastec, Sensodyne, and MSA, which is a different system. You use different pumps. You use Dreger pumps with Dreger tubes and the other system with the other tubes. Now our pump has a stroke indicator here. It's white when the pump is open. This is the bellows open. And it turns clear when when it's doing a stroke. Here's a stroke counter. To be honest, the stroke counters don't work very well on these tubes. The idea is this plate is supposed to hit this and advance the counter, but that's the way it is. Also, you've got a tube cutter on your tube. We don't actually use those. We got some nice handheld ones that work a little bit better. So the first thing to do, you have to periodically calibrate your stroke volumes, make sure they're at 100 mils. And every time before you use the pump, you should do what's called the leak check. You take an intact tube. Notice this tube has not been cut. The other end has not been cut either. You stick it in the tube and you squeeze the bellows down and you wait for about 10 minutes to see if the bellows expand or not. If the bellows expands, your pump is leaking, you're going to set that aside, you're going to try another pump. So here's some example of those active sampling tubes. You know, you can see where the glass was cut. You can't see the other end of those, but the other end is cut as well. The samples were drawn through. If you notice, this doesn't quite, the color stain front, it might get there or doesn't quite get to the stain front. If it doesn't, if the stain front doesn't get to that first marking, since we don't know how much it takes to get the initial color change going, all we can say is it's less than the minimum marking. On the other hand, if it goes and changes the complete tube, so it changes from that orange, yellow orange to this black, all I can say is it's off or greater than. In this case, you can see here's my N. N is the number of strokes the tube uses. And in subsequent pictures, you can see this tube has a 10-stroke scale and a 1-stroke scale. Notice there's a difference in the units. The arrow always indicates to me which direction my airflow is. These are all intact, unopened tubes. And then my units of scale are down here at the bottom as well. So when I use these tubes, I need to make sure I know how many strokes were used, so I have the right scale reading. And then I also need to make sure I get my units of scale. Remember, with our passive monitor earlier, it was in percent hours, which I then have to divide those hours out with the length of time to get a concentration in percent. In this particular tube, it reads in ppm, and it's an active sample, so I'm going to have my concentration based on the direct reading off the tube. So for collecting our ammonia sample, here's the instructions to go through. It tells you the reactions and the range for the 10-stroke versus the 1-stroke scale, what the standard deviation is, what the color change is. It says blue, it looks black to me, and some limitations on that reaction. This is the little glass jar that we use. We put the little napkin down in it to kind of increase the surface area to make sure that we have enough in the air. What we use for our solution is simply a household clear ammonia solution. We collect that sample at the mouth of the jar. You can see the color change starting to occur here. If I were to stick this down in the jar, the concentration would be so high that it would go off scale, like we saw earlier. If I leave it near the mouth, I'm really getting the concentration as it comes out of the jar. So this is all the same tube. It's multiple shots to kind of show you it as you rotate it around. The sample we collected was on the 1-stroke scale, so I want to read my final reading on this 1-stroke scale, even though I can see the 10-stroke scale here. But I need to kind of estimate about where I think that color change is, and so I'm kind of showing you as it rotates where the edge of that color stain is, and that's going to be my reading. So I'm going to estimate where the front is and then where it is approximately between my scale markings. And remember, my units of scale are ppm again. So that's the data for table 5.2. And then part B, we're going to use this tube. And again, these are all intact tubes. You can see that both ends are covered. This is a carbon dioxide, 1%. And by the way, in German, commas, like you see the comma here, that's a decimal place. So that is 3.0, 2.5, 1.5, not some other funky measurement. Or on the 5-stroke scale, it's 0.1, 0.2, 0.3. And the units of this scale are, again, percent volume. So this one has a 1-stroke and a 5-stroke. It reads in units of percent volume, and here's the actual tube designation. And here are the instructions. You can see here's that tube designation again. The instructions that show you the range for the two scales, 0.5% to 6 for the 1-stroke, 0.1 to 1.2 for the 5-stroke. Here is the tube that I actually want you to read. I have a highlighted version. I failed to take multiple shots of that, and the tube got blown away before I had a chance to go back and take more pictures to let you see it a little better. But it's on the 1-stroke scale here, and your reading's pretty close to the marking anyway, so it should be fairly easy. Just make sure you pay attention to your units, right? So what we do is we light a candle, let that candle burn out, and then we connect the tube and we collect our sample out of that bell jar, looking at the level of carbon dioxide after that candle burns out. Here's a blown up version, so you can see again, there's your stain front, your color change. It's on the N1 scale, which is the one I want you to read it on. And this will be the data for your table 5.2. And then the next one, this is moving past. Part 3 is a description of how to calibrate the gas meter. We demonstrate that in class. We don't actually do it, but it's basically a 2-point calibration. You don't really need to worry about that too much, other than it's a 2-point calibration that might help you with your theory a little bit. We hook up a Polytech 4, which is a screening tube that's got these different colored layers, and we collect the from our bag sample that was collected from auto exhaust. You can see an intact tube here that corresponds to, there's your blue, there's your yellow, there's your white, kind of gets off a little bit. There's your blue for layer 4, white, yellow, and they say purple, it sure looks pinkish to me. And actually their blue looks kind of purplish to me, but you know, that's the way they label it. So this is what the tube looks like before the color change occurs. Now, if you have a color change, you have, based on whether it's the whole air or the inlet, an estimate of what the concentration might be. Okay. And then you're going to record based on the color changes, which in the tube that that's coming up, what we think is there. So here's our tube. You can see this is a 1-stroke tube as well, our Polytech 4. Here's the unopened tube. Here's the one that was exposed for the lab. This is your data for table 5.4. You can see you get a color change here and a color change here. It's not quite the whole air. It's mostly on the inlet side. And there's really not a color change on these others. So I really only going to have a color change on 6 and 7. On 6, I have change to black brown. I don't really have the gray or the yellow orange. And on the 7, I have that color change to brown, which is an indication that I have the carbon dioxide, and then these other substances that are black-brown color change. And the next, I'm going to take a carbon monoxide tube. Notice this is a Gastech system, not the Draeger system. The tube that we're going to use here is a 1L carbon monoxide tube. It has a 1-stroke scale. We used 1 stroke. It's designed that you can use multiple strokes and then adjust or correct based on that, but we're simply using a simple 1-stroke scale. And so here's our tube. Again, this is the intact tubes that have not been opened yet. You can see it's a 1H. It's got a 1-stroke scale. It's in percent volume. Here's your readings. Since it's made in a country that uses a decimal rather than a comma, you can see 5, 4, 3, 2, 1, 0.5, and 0.2. So here is your tube that we opened and exposed to that bag sample. Again, it simply is a 1-stroke scale. It doesn't vary. You can just kind of see where that stroke, it falls pretty close on, maybe slightly below the 0.2, which is the first scale marking on that tube. And you can record that as your data for table 5.5. Now, when we calibrate a gas meter, it's a 2-point, we zero it, and then we calibrate it against a CalGas. This is a CalGas that you could use for this sort of monitor. It's got 4 sensors in it. It looks at hydrogen sulfide, carbon monoxide, percent LEL. In this case, our CalGas has it 50% of the LEL, or 2.5 of the 50% of the LEL as methane, oxygen, and then nitrogen for the balance. Notice our oxygen, when we zero it, we don't really zero the oxygen. We let it go to natural background, which is usually 20.8%. And so we're concerned about oxygen dropping, so that percent drops. So the range we're calibrating it is the 20.8 natural background on down to that 12%, so that it covers the 19.5% that I might be concerned about in an oxygen deficient atmosphere. So I'm calibrating, I can say that my instrument's accurate as long as it's reading between 0 and this reading, because I know that's linear. When it goes beyond that, the sensor may give me a reading, but I'm less certain about the accuracy of that reading. Okay. You'll need to answer the questions that I get you to get your lab data. That's going to give you the time for that passive monitor in table 5.1, and I'll give you your data for your direct reading instrument. Basically, we took the direct reading instrument and put in that same bell jar that you saw the candle in, and flushed the bag sample over it to see what the concentrations were. That's table 5.6. And then you'll have the data for practical exercise tables 5.7 and 5.8 that you need to be able to do the calculations for your predicted and your percent errors. This lab does have a write-up with it. The write-up only needs to cover through data table 5.6, which is the ones that have concentrations. When you do your write-up, think about it as if these were simulated workplace atmospheres. If I had a worker exposed to the concentrations I see in these tables from table 5.1 to table 5.6, what sort of problems might I anticipate, what health hazards might be there, and what sort of actions might I need to take to correct or protect my worker from those. With practical exercise 5 is more practice to try to get that gas and vapor down a little bit better, combined gas law. You'll get a lab assignment grade for that, along with answering the questions in the back. And you might look at the questions as they apply to the first 4 parts of the lab and what we're doing there, and see, does that kind of give you a hint to what I need to be putting into my discussion part of my lab. So hopefully that'll help you understand what's going on a little bit better. If you have any more additional questions, feel free to post them on Blackboard or send them to me via email. It helps to post things on Blackboard because if you have questions, other people probably have them as well. And so people are more likely to post and read those, and everybody can see those answers, which is helpful to them as well.